Faraday's law of electromagnetic induction tells us that if we have a changing magnetic flux through a coil, we have some EMF generated in the coil, and which in turn generates a current in that coil. Now this could be our coil here, and we can have a magnet here, a bar magnet, and if I move this bar magnet, I would change the flux through the coil, because let's say if I bring the magnet closer to the coil, I would increase the field at this point would become stronger, and so the flux through the coil would increase, and that is a change in flux. And Faraday's law tells that EMF, I hope that, yeah, right there, EMF equals minus d phi by dt, which simply means that the EMF in this coil would depend on the rate of change of the flux through this coil, right? Now Faraday's law tells us the magnitude of the EMF generated, and if you know the resistance of this coil, the whole loop, we can find the current through the loop. But this law does not specify anything about the direction in which that current would occur. So does that current occur in a clockwise direction or an anti-clockwise direction? In this video, let us try to figure that out. Yeah, so let's assume that I am bringing the magnet closer to the coil, and in doing so I am increasing the magnetic flux through the coil here. Now due to that, let us assume for now that we get a clockwise magnetic field. Let's assume that we get a clockwise current, right? So this is the clockwise direction, so we get a current in this direction, right? So as I bring this closer, the flux through this increases, and we get a current in this direction. I'm assuming that for now. Now let's check if our assumption is correct or not. But the thing that we need to keep in mind at this point is that a current carrying loop itself generates a magnetic field. Well, that is much like a solenoid. A solenoid is nothing but a collection of loops that have current through them. So a collection of current carrying loops that generate magnetic field. So even this loop, because this is a current carrying loop now, this would also generate a field of its own. Now let us try to figure out the polarity of that loop. Now I can use the right hand thumb rule for that. I point my thumb in the direction of the current, and I know that the magnetic field lines would wrap around this section of the wire in this manner, which means they would go in this direction inside the loop, and they would come out like that. So I just used to clarify here, the current carrying loop is oriented in this way, right? So it's the current that I have assumed is going like this in this direction, and the magnetic field of this loop itself is going in through here and coming out, and like coming out from that side and looping back in. So that is the direction of the magnetic field in this particular case, if this is the current. Now how are the magnetic field lines of a bar magnet? So we know that we can consider this current carrying loop as a very small magnet, right? As a magnetic dipole, or a small, very small magnet. And what is how do you imagine the magnetic field lines of a magnet? So this is the south pole, this is north pole. The magnetic field lines actually go from north to south, right? But they have to loop back, and so they inside the magnet they come back from south to north. So that is the key thing. Inside the magnet they go from south to north, but outside they go from north to south, right? Simple as that. And they loop back, go from south to north inside the magnet. So inside the loop, which is like inside the magnet, they should go from south to north, south to north. So this side is like the south of the coil. So if this is the coil, this side should be the south of the coil, and that side should be the north of the coil. That's why they're going from south to north, like through the coil. So this side, the top side of the coil is south, and the other side is the north. Now if such a thing happens, what would happen now? Let's say I was bringing it closer to the coil, and the current generates in this direction, we get a magnetic field in this direction going through the loop, and which means we have a kind of a south pole on this side and north pole on that side. But this south pole would now attract the north pole, and the magnet would start moving towards the coil even faster because the south pole is attracting. And now because it is moving even faster, the flux through the coil would change even faster, would increase even faster at a faster rate. And because EMF is the rate of change of flux, and now flux is changing even faster, the rate of change of flux is increased, the EMF would increase. And as the EMF would increase, this current would increase, and if the current would increase, the magnetic field would increase, right? And if the magnetic field through this would increase, the south pole and north pole would get stronger, and the attraction between this south pole and this north pole would get even more stronger, and this magnet would be attracted to this south pole even with a greater force, and so it would start moving with a greater velocity. And if that happens, then again, because this is now moving even faster, right, so the change in flux would be even more higher, and this loop would continue, right? Now the flux would increase and the current would increase, and the magnetic field strength of this loop would increase, and this would move even faster, and it would continue to move faster and faster and faster because of this chain effect. Now if you look at the broad image of what's happening, I'll just remove this for now. What would you observe actually if this happens? You would observe that even if I give a slight push to this, that should start moving the magnet, and that should induce a small current in this direction. That would induce a small magnetic field, which would then pull it towards the coil, and that would again increase the current through the coil, and that effect would keep on increasing. So even if by giving a small push, the magnet should accelerate with a very large velocity towards the coil. But we know that simply violates the law of conservation of energy. Where is that extra kinetic energy of this bar magnet coming from? And also, because there is such a high amount of current, the current keeps on increasing, right? High amount of current, we get a high amount of heat released through the wire. H equals that equation. Heat depends on the current flowing through the wire, so we would get a lot of heat released. But where is that energy coming from? The kinetic energy of this bar magnet and the heat released from here. It's just coming magically from somewhere. But we know that heat energy cannot be created from nothing, right? It should come from somewhere. So obviously this situation is flawed. We are getting free energy from nowhere, and that is just not possible. So this scenario violates the law of conservation of energy, because we are getting free energy from just nowhere, right? Nothing is losing energy, but we are still gaining energy. This is gaining energy, this is also producing energy, and nothing is losing energy here. So this is violating the law of conservation of energy. So what we now can infer from that is that this direction that I've assumed of the current, that is wrong. So which leaves us with only one option, that the current must flow in this direction. Now let us bring the magnet in that direction. Let us move it in that direction. The flux through this is increasing, and we get a current in this direction. Now when we get a current in that direction, if I point my thumb in that direction, we know that the magnetic field lines would loop around this section in this way, which means we would get a magnetic field coming out of this loop like this. So it should come out of the loop like this, and because you know that magnetic field lines inside the magnet go from south to north, so this would behave like a small magnet which is north on this side and south on that side, and this north would repel this north. So when I push it, I would have to do work to bring this magnet from here to here. So I have to actually perform some work to increase the flux through this coil, and because I am doing work here, I am losing some energy, and that energy is being converted into the heat energy that is being released through the current flowing in this loop, and that is perfectly in line with the law of conservation of energy. No energy is being created or destroyed, and that makes a lot of sense to me. And yeah, that is so. Now we can understand that we need to do some work in order for some current to be generated. And that is how that is where the heat energy is coming from. It is coming from the work that I do in moving this magnet against the magnetic field of the generated by the loop. So this is Lenz's law actually that we've talked about. Lenz's law, and his law is simple yet complicated. His law simply states that in such a case, when we have a changing magnetic flux through a coil, be it increasing magnetic flux or decreasing magnetic flux through a coil, the current in the magnetic loop would be generated in such a direction so as to produce a magnetic field that opposes the change in magnetic flux through the coil. I'll repeat. If we have a changing magnetic flux through a coil, Lenz's law states that the current in that coil would be generated in such a way, in such a direction, clockwise or anti-clockwise, such that the magnetic field generated due to that current carrying coil opposes the change in magnetic flux. So if the magnetic flux is increasing, for example, when I was pushing it in this direction, the magnetic flux through the coil was increasing. So now the current has been generated in such a direction, in an anti-clockwise direction, such that the magnetic field of this loop is trying to oppose the change in flux or trying to stop this magnet here. Similarly, if I were to be pulling this magnet backwards, the polarity would switch of the current. We would get a clockwise current and we would get a field in that direction, and that field would actually attract the magnet or try to stop its motion or stop it from being pulled away, right? And in that way it is trying to avoid the change in magnetic flux through the coil. So I hope you now know the basic reason behind it. The actual reason behind it is the law of conservation of energy. But to visualize this law better, we can say that this coil just doesn't want a change of magnetic flux through itself, and so it avoids a change in magnetic flux through itself. And it would do so if given it would generate the current in such a direction so as to oppose that change in magnetic flux through the loop. And yeah, you can use a bit of common sense to answer questions based on that. That's it for this video.